I'm Minidu Hayawasam, a final year undergraduate at Informatics Institute of Technology affiliated with University of Westminster. My project title is Boosting the Exploration of Reinforcement Learning Agent through Human Demonstrations. Reinforcement learning is a computational approach of learning by interaction. In typical setting, the ultimate goal of reinforcement learning algorithms is to train a model to find the optimal strategy to solve the problem by achieving maximum reward. The reinforcement learning agent do this by exploring the surrounding environment by taking random actions and improve the behavior by gradually toward the direction of optimal reward. In most scenarios, since the agent is ignorant and performance is significantly poor at the beginning, but as the agent learns, it reaches almost a superhuman level. But before the agent reaches a desirable level of performance, extensively large number of environment samples are required. When it comes to exploration in reinforcement learning environments with sparse reward signals, this problem is exponential, especially in long horizon tasks with complex state and action spaces, which makes the applicability of reinforcement learning in real world problems out of practical reach. The research contribution of this proposal is to introduce a novel human knowledge-driven exploration strategy in order to boost the learning rate of the reinforcement learning agent. The novel approach is developed with considering most common limitations on this area, such as accounting the suboptimality of demonstration, overfitting of learned policy to demonstration policy, sample efficiency. The proposed algorithm will be an extension of work done on the DDPG or the Deep Deterministic Policy Gradient algorithm. This proposal suggests an experimental evaluation of training performance of standard DDPG arithmetic model versus human knowledge combined arithmetic method. In the research work of pre-training deep actor-critic reinforcement learning algorithms with expert demonstrations, the expert data is used to pre-train both policy function and value function simultaneously with baseline gradient and pre-trained gradient. This model is tested upon DDPG and ACR and proven to outperform the baseline algorithms. Major drawbacks of this approach is if the demonstrations are suboptimal, the overall training performance might significantly lag or might prone to converge on local optima. This algorithm is successfully proven in low-dimensional simulation tasks with dense reward signals. The research work of deep deterministic policy gradient from demonstrations is closely related to the research work of deep Q learning from demonstrations in optimization techniques used, but built upon the policy gradient framework of DDPG. In both algorithms, the concept is to use both self-generated and demonstration data to motivate for expert-like behavior. In talking about optimization techniques, it uses a secondary memory buffer to save demonstrations data with prioritized replay memory. So when sampling data, more priority is given to demonstration data rather than samples collected by reinforcement learning agent, resulting in a more efficient propagation of the reward information. Second, it uses a mix of 1 minus step and n minus step for adjusting parameters of the critic network for sparse reward. The result is incorporation of n minus step returns as it's the propagation of Q value along the episodes. Third is updating the model parameters multiple times per time steps on each trajectory. Finally, using L2 regularization on model parameters on actor and critic in order to stabilize the final learning performance. In DDPFT, when collecting demonstration data, researchers have used a human expert to kinesthetically force control arm using Sawyer robotic arm. Some limitations of this research work can be found as not having a mechanism to account for suboptimal demonstrations since demonstration data are collected assuming they are optimal. The research work of overcoming the exploration in reinforcement learning with demonstration, offline pre-training with online reinforcement learning is used to transfer expert knowledge to learning policy. This also adopts the DDPG algorithm and combines optimization techniques such as demonstration buffer prioritized replay used in DDPFD. It differs from DDPFT in that in order to encourage imitation on given demonstrations, the objective function is augmented with behavior cloning loss. To address the suboptimality issue with demonstration, a Q-filter mechanism is introduced, so only demonstrations with higher Q value are chosen for loss penalty. Furthermore, to avoid issues associated with long horizon tasks such as sparse reward, it employs a technique as when restart episodes randomly resets from goal and states from demonstration data. This approach is successfully proven to be able to solve complex multi-step tasks. A major limitation of this algorithm is on solving complex tasks, the sample efficiency decreases. Therefore, a large number of experiences are needed to collect in some setting. It might be impractical in scenarios such as running on physical robots. Another limitation is although using a behavior cloning loss significantly improve the learning, since this loss always tied back the actor with demonstration network. Improving of learned policy beyond the demonstration policy is avoided. As a result, the learned policy might suffer from overfitting. The research gap the proposed work going to address can be summarized as evaluate state-of-the-art learning from demonstration algorithms based on policy gradient reinforcement learning frameworks and compare and contrast them to identify limitations of existing work. Then evaluate state-of-the-art policy-gradient algorithms based on actor-critic architecture since almost all of the current models are built upon existing reinforcement learning algorithms. Third is identifying tasks that exploration is challenging and test the model on those tasks. This low-level architecture diagram is used to explain the training process of the complete system. All the components belong to baseline algorithm are illustrated in black color and the rest are research components. In the new architecture, the training process happens in two phases. The first phase can be mentioned as learning from demonstration phase and the second can be mentioned as the reinforcement learning phase. Before starting training the model, the demonstrator needs to initialize how many episodes that he is going to interact with. Then the model first goes through the LFD phase and there the human expert interacts with the environment directly and demonstrations are directly saved inside the memory buffer. So the Both demonstration network and critic network will be trained as in parallel version of DDPG with hindsight experience replay technique. Once the LFD phase is done, the reinforcement learning phase starts simultaneously, and during this phase, both actor network and demonstrator network chooses actions according to the current state, and the action evaluator chooses the action with highest Q value between two policy networks, and that action will be executed in the environment. During this phase, the parameters of the demonstrator network are kept frozen. The high-level architecture of the system is presented here. Since the new architecture is built upon the baseline version of DDPG algorithm, new research components are highlighted in red color. They can be identified as the demonstrator network and action evaluator. The complete system has 6 neural networks. 4 of them are from baseline algorithm as online and target networks, and rest of the 2 are demonstrator policy network and its target network. If we talk about the demonstrator network, it is trained during the LFD phase by replacing the agent by the human expert and collecting data coming from the input device directly. Then, the partially pre-trained network is used to support exploration of learning actor policy through action evaluator mechanism. During this process, the weights of the network are kept frozen, allowing learning policy to improve beyond the demonstrator network. So, the methodology of transferring expert knowledge to actor policy happens in two stages. Since the demonstration policy is influenced by the expert behavior, the human behavior is transferring to the learning policy in a soft manner. The parameters of the demonstrator updates multiple times and use a higher learning rate to speed up the gradient ascent and get the maximum knowledge out of demonstration data. Furthermore, unlike policy network, the demonstration network does not use a noise function. When we discuss about the action evaluator mechanism, the action evaluator mechanism of the algorithm is driven by the critic network, which is used to bridge the actor and demonstrator network, accounting imperfectness of expert data. The partially trained critic network during the LFD phase used during the reinforcement learning phase to choose more rewarding action between two policies. This is done by taking the actions of both policies and states as the input and output as the Q value by forward propagating the critic. In our work, Q value is used to determine if the demonstration policy should override the ignorant learning policy to boost the exploration. In a summary, in this new architecture, critic is playing two roles as to calculate the policy loss and determine the quality of demonstrations. Finally, both demonstration data and self-generated data are saved into the same memory buffer. So the random sampling strategy of the critic will sample from expert data more frequently in earlier episodes during the RL phase, and as the training progresses, the critic will sample more from self-generated data. So compared to related works not using a secondary buffer with prioritized experience replay, this new technique will ensure the learning policy and demonstration policy is not tight coupled, and learning policy will not overfit to human expert behavior. This is the reason that the model could ensure the convergence with slight performance lag even with completely suboptimal demonstrations either. The code of the actor is displayed here. The primary objective of the actor is to map state space directly to action space. The demonstrator network is an instance of actor. Therefore, implementation and design-wise, demonstrator network is identical to actor network, but the demonstration policy network uses a higher learning rate in order to reach the global optima faster during the LFT phase. When we talk about the network architecture, actor uses three hidden layers. The input layer density of the actor is number of states, and the output layer density is number of actions. The code of the critic network is displayed here. It has three hidden layers. The input for the critic network is action and state. Since the algorithm is focused on multi-goal reinforcement learning, the goal is also taken as an input. The implementation of the action evaluator mechanism is displayed here. The action evaluator takes the state, goal, actions chosen by learning actor policy and demonstrator policy. It calculates the Q-value for the actions of both policies by forward propagating through the critic network and determines the action with higher Q-value. The action with highest Q-value will be returned to the environment. The training rollout during the LFD phase is almost similar to the reinforcement learning phase, but the agent is replaced by the action chosen by the human expert via input device. When training the model with parallel processing setting with multiple MPI workers, the master node is allocated for the human agent and slave nodes iterates as in reinforcement learning process. This is the later part of the implementation of learn from demonstration phase. to test the new model with sparsely rewarded multi-goal environments, which is the scope of this research. We choose Fetch Robotic environments provided with OpenAI Gym powered by Mujugo Physics Simulator. Each environment task need to be solved in 50 time steps. In the reward function for each time steps beyond the desired goal is punished with a score of -1, and for each time step reaching the achieved goal within 5 centimeter range of tolerance to desired goal is awarded as 0. The objective of this testing is to validate that the novel approach is capable of converging and train the agent to solve the task outperforming baseline. This test was performed on all the robotic environments. On each testing, the graph on the top represents the quality of demonstration collected with success rate over 100 episodes of demonstrations. The graph on the below represent the success rate over epochs against the baseline algorithm. A summary of test results are shown here. The results show that on each task, the new approach was able to significantly outperform the baseline algorithm successfully. In this test, the human demonstrator was replaced by random sampling actions, which is a built-in function of OpenAI Gym. The expected outcome is to intentionally reduce the performance of demonstrator policy and train the critic by adding completely suboptimal data to the memory buffer. The purpose of this test is to evaluate the robustness and prove the model performance does not go significantly beyond the baseline of DDPG, with the worst case of totally suboptimal demonstrations, and still the model can maintain the training performance and converge. These test results reflect how well the new model can deal with imperfect expert data and learning policy does not overfit to demonstration policy or data. Since these sparsely rewarded multi-goal tasks are intensively long horizon, researchers are highly recommended to use distributed machine learning techniques on training models on these tasks. The purpose of this testing is to evaluate how the training time and number of episodes taken to converge varies with the new approach with serial processing versus parallel processing. When the learning curves are analyzed, it is obvious that while the baseline algorithm learns nothing during all the epochs with serial processing, the new algorithm manages to maintain a learning curve almost similar to the learning curve with parallel processing. This testing reflects the sample efficiency in suggested new model architecture. Conclusions of the research work carried out are summarized below. First, that transferring the knowledge of expert through a pre-trained network in soft manner is more stable than directly initializing model parameters. The Q-value output of the critic can be used directly to determine the quality of demonstration data successfully. Using a single memory buffer is more efficient than using two in terms of resource utilization and minimizing the overfitting bias. Finally, in this novel approach, even a non-technical human expert can play the role of human demonstrator. Finally, future works of the research work carried out can be mentioned as testing the applicability of new optimization techniques on other variations of DDPG and other variations of policy gradient algorithms based on actor-critic architecture. Next, the research more on how to adapt this technique on solving real-world problems such as autonomous driving, financial applications, and etc. More on improving the quality of demonstration and reducing the quantity of demonstrations provided, maintaining the same learning efficiency.